Hey y'all, this is the ULA Andrew for Orgo 2, and I'll be going over a couple problems regarding splitting patterns, regarding signals, and some of the questions we went over this Thursday that we weren't able to cover actually, from the 1 to 25 questions. So without further ado, oh Lord, let me get rid of that. Okay, so with this question, I'm going to pose how many signals are there? Number of signals, and what does the splitting pattern look like? Okay, so the first thing I like to do is I like to look for any stereocenters, anything that could throw off the protons from being diastereotopic from each other. And so over here we don't really have any dash chlorines or wedge chlorines, dash bromines. All we have are the um, oxygens here, which they're in plane, so they're not going to pose any threat to the protons. And so looking over here, I try to go for the easy stuff, aka the methyls. And so we're going to expect signals over here. We can always do the replacement test. I'll check to see if I can do that later. But we'll go on to these methylenes real quick. And so if we were to split this in half this way, will the dash part be the same? The wedge part be the same as the dash part for these hydrogens? Why or why not? Well, if we don't know that, we could always do the replacement test. And so I'll go and do that right now. Let's see. And so I'll put this as an X, put this as an X. And so all we got to do is we got to get a mirror image. I'm going to duplicate this. We're going to spin, we'll do, this is molecule A, this is molecule B. We're going to turn this into B prime by spinning this whole molecule 180 degrees. And so we will get this. Okay, so if we were to put a line down the middle. Okay, so do these line up? Are they superimposable? Superimposable. They are not superimposable. Are they mirror images? Yes, they are mirror images. Therefore, they are enantiotopic. Therefore, the signals will it'll count the same. So over here, we'll put H. Okay, let me actually 1, 2, 2, 3, and you can do the replacement test for these hydrogens as well, but they will be the same signal. So, well, let me just write this out. H, H, and then 4. Okay, let me actually change the numbering because that's just kind of all over the place. 3, 3, and 4. Actually, let me not H, H, H. I'm not going to shortcut. Because if you were to do that in the exam and just circle the methyl, you probably wouldn't get any points for that. Four. And so I will move this over here real quick. Okay. And I'll give you a few seconds, or I'll make sure everything's in frame at the end once we're done with this. Okay. And so let's see the splitting pattern for H1, H2, H3, and H4. So H1, all these count as one signal. We also are not factoring in H1 into our signaling. We're looking at the carbon that's connected to H1, and then we're looking at the adjacent carbon. How many protons are connected to this carbon? 2. Okay, n plus 1 rule, so we add 1 into 3. 3 is a triplet. So if we go to 2, we go to see this is the adjacent, or not the adjacent, this is the carbon that contains the protons. Then we look at the adjacent carbon, and we realize that there are 3 protons plus 1. We get 4. This is a quartet. So whenever we go to 3, we look at the carbon that's attached to these protons on H3, and then we look at the adjacent carbon. We find out that there are 3 protons plus 1 rule equals 4, quartet. So if we go to H4, we check to see the carbon that is connected to all 3 protons, check the adjacent carbon. I realize that there are 2 protons attached to this carbon. Therefore, it will be 2 plus 1, and plus 1 rule, 3, which is a triplet. And I'll put all this just for a second. Okay, let me see. Over here. Okay, and so these are some of the questions we weren't able to go over. Are the 3 hydrogens that are shown homotopic? We can try and do. We don't really have to do the replacement test because, I mean, yeah, we could do the replacement test. Oh, I already put the answer. That's cool. But it is correct because this sigma bond has free bond rotation all throughout the bond, and so as the carbon is spinning, will I be able to point out this hydrogen from this hydrogen from this hydrogen? No, they all look the same. And that goes with the general rule that all methyls will be homotopic. And so, yes. What is the relationship between the hydrogens that are shown below? Okay, so over here, one of the things I try to do is right now I'm on iPad, so I could use this as the in-plane bonds, and I try to cut this molecule through the bonds in half. And so with the proton over here, we have a dashed proton and a wedged proton. I always get that confused. Then we have a dashed proton. I'm just going to as to show that this is one side and then this is the other side. I can do left, right. And so, let me see. So we have a chlorine over here. This chlorine is not very fun because this is the deciding factor between if H1 and H2 are anisotropy. And because there's a chlorine on one side and it is not counterweighted by another chlorine on the other side, aka if there was a wedged dashed chlorine, this makes the hydrogen here and here different. Kind of just jumbled everything up. Let me just do this. These are different protons. And therefore, considering they are different protons because of the chlorine being on the wedged side and a hydrogen being on the dashed side, this is diastereotopic. Okay. 17. How many signals are there for the following compound? So, as of right now, it looks like the oxygens are in plane, and it looks like the bromines are in plane. But wait a second. Can 2 bromines be in plane? With this carbon bond being in plane as well? No. Therefore, we can delegate this bromine, as a wedge. And we can delegate this as a dash as well. And so looking over here, how many signals are there? Okay, there's one signal over here. I mean, there's one proton over there, and it's covered with two bromines. It's going to be a very distinct signal. And so we have one H over here, or we have a methyl group over here. We already know that these three are going to be the same. And so then we look over here. Are these two protons the same or different? Give you a few seconds. God bless it, the damn answer. Hope you guys didn't look at that. But corresponding to the answer, these are the same signals. And some of you may be like, what the heck? Andrew, there's a bromine on a wedge. There's a bromine in plane. Isn't that... How could a bromine on a wedge and a bromine in plane compare with these two protons? So, the cool thing about organic chemistry is that you can rotate the bond a little bit. And so, if you are to rotate... Actually, no, not... I mean, you could rotate this bond, but you can rotate the carbon specifically. You can move the carbon... You can move the bromine to the wedge position, the wedged bromine to the dash position, and the H to the in-plane position. And so this is how it would look. It would look like H, Br, Br. And so if we have two Brs on wedges, or if we have a Br on a wedge and a dash, and then we look at these hydrogens, we find out, okay, they have bromines on both sides, then we're fine. There's nothing, everything is even. There is symmetry between this molecule. Therefore, we have signals 1, I'll just delegate these as signals 2, and then change this up. Signals 3. And so, even though the question didn't ask it, what are the patterns going to look like? So, if we go to H1, let me get rid of all this junk. If you need a couple more seconds to look at that diagram, you can just always go back in the video. And so we have H1, we have this carbon connected to this carbon, and if you're also confused about the adjacent rule, all you have to think of is the proton has to be 3 bonds away from another proton. And so over here, we have 1 bond, 2 bonds, 3 bonds. 1 bond, 2 bonds, 3 bonds. Are there any hydrogens here? No, there are not. So we can only go over here. And so, how many protons do we have? And over here, we have 2 plus 1 equals 3. This is a triplet. And so, if we look back on, if we go to H2, check to see, okay, this carbon, check to see the adjacent carbons. This one does not have any hydrogens on them. We look at the left one, there's 1 proton, so 1 plus 1 equals 2, doublet. And so then we go to H3, okay, there's not any hydrogens over here. I mean, that's not even a carbon, this is an oxygen. And so we could try to do 1, 2, 3, there's still no hydrogens over here. So it will be, how many hydrogens are there? 0 plus 1, it will be 1, it will be a singlet. And so, in general, there's going to be 3 signals. What is the splitting pattern for HA? Okay, so let's go put this as a wedge. Let's go put this as a dash. Okay, so we could do the replacement theory But also, is there a bit of symmetry here? There is indeed. So, if you look down in plane, there's symmetry right here. All the half to the right, which would be the dashed side, and the side to the left, the wedge. Oh my lord. Wedge side is to the right, dash to the left. If you're looking at it the way that I'm looking at it, the sides are perfectly symmetrical. Therefore, HA and HA over here are fine. We have to make this clear because if HB, if these protons were different, then our splitting pattern would be different. But luckily they are not. So, those both are the same. So, we look at the carbon over here. Look at the adjacent carbon. Are there any hydrogens there? No. Are there any hydrogens here? Yes, there are 3 hydrogens. Okay. Are they all distinct or are they all the same? It's a methyl group, therefore they're all the same. So, HA, how many protons are there on HB? 3 protons plus 1 equals 4 quartet. What is the splitting pattern for HC? Okay, let's look over here. Let's do this. Okay, so unfortunately, because of this outlying methyl group, there is no symmetry. So we may have to do a replacement test, and it doesn't hurt to do the replacement test. Okay, so I'll put, what am I doing? Okay, do this X, and then yeah, I don't know why I got rid of that. Oh, excuse me. So we have X over here, boom, 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 and so what we have to do is we have to flip this 180 degrees to get this. Let me actually move this a little bit to the left. Boom, 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 boom. Okay, and so when we are flipping this, the wedge is turning into a dash, and the dash is turning into a wedge. I don't think I necessarily expanded on that when I was rotating the molecules. I'm sorry about that. But that is what happens. And so 1, 2, 3, 1, 2, 3. Okay. So we have H, X. So what are the relationship between these molecules? Are they non-superimposable? Well, yes. No. They are not superimposable. Are they mirror images? Yes, they are mirror images. Therefore, they are enantiomers. Okay, enantiomers help because these both are the same signals. Okay, what is the splitting pattern for HC? We'll look at this carbon that's on the protons. Look at the carbon connected to the ketone. Well, connected to the carbonyl, I should say. And there are no hydrogens on this carbonyl. So we check to the left of us. We check to see H and H. And if you are to do the replacement test, they will be the same. Especially since, like I said, there's symmetry straight through the molecule. So these would be, I'll just say HB, HB. And so how many protons are there? 2 plus 1 equals 3. Tis a triplet. Okay, and time for the hardest question of Orgo 2. If you do not know the answer to this question, I don't know if college is the best route for you. And with that being said, guys, it's obviously 4. Goodbye.